So now we delve into the core Paxos algorithm. So we have first a terminology for Paxos. In Paxos, you have a number of roles in the system. You have proposers. They will attempt to impose their proposal on a set of acceptors. Then we have acceptors. This is a set of processes that may accept a value issued by proposers. Acceptors is really the memory of the consensus algorithm. And then you have learners. Learners are those who learn a decision of a proposal. And they will decide depending on what the acceptor set has accepted. So these are actually roles. They are not processes. And each process in our normal setting that we presented all the algorithms in this course, each process will play all the three roles. So a process in our algorithm will be a proposer, an acceptor, and a learner. In practical systems, you might have a smaller number of acceptors, and you have a larger number of proposers and learners. So acceptor could be 3 or 5 only, and learners could be an arbitrary number. And the same for proposals. So let us now develop the algorithm step by step. So we are attempting to solve the problem step by step. So here is a naive approach first, so that everybody knows that it will not work, is that we have a centralized solution. What is a centralized solution? As I told you, the acceptor is the memory of the consensus. So we assume we have one single central acceptor, and a proposer sends values to the central acceptor, and the acceptor decides on the first value it gets. This should work, except we are in a course on fault tolerance, and the acceptor is a single point of failure. Once the acceptor crashes, we don't know what's going to happen. So this does not work. Our solution is then the Paxos algorithm, which is a portable consensus. And what does it do? It decentralizes the acceptor. So proposals are going to talk to a set of acceptors, and that will tolerate failure as long as a majority of acceptors do not fail or are not faulty. So acceptors might fail, but you need only a majority of acceptors for surviving. And depending on the failure model, if it's a crash stop model, so failing means you just get out of the system, whereas if you're in the fair recovery model, you might fail and then recover. As long as you recover finitely many times, you are still a correct process. And proposers might fail to impose their proposals, and in this case, they will abort. So this is our setup now. A set of acceptors. These, as long as a majority are correct, the algorithm works fine. And a set of proposers, they might propose, but some of them, they might fail to impose their value and they abort. That's it. So in effect, we are using a quorum approach here. Each proposer tries to impose its value V on a set of acceptors. And now we come to a very important concept, the concept of when we can say that a value is chosen. So if a majority of acceptors accept a value V, we call V is a chosen value. The chosen value will be the value that will be decided upon. And learners will always try to decide on a chosen value. So this is one of the basic ideas of the algorithm. To understand this algorithm well, we have to look to the concept of ballot arrays. Ballot arrays or round arrays is a table where the ballot array represents the state of the acceptors. So here we assume a set of rounds, and each row describes one round. It describes the state of the acceptors at a certain, say, snapshot or a round. Each acceptor is initially have some initial value, which means there is no value proposed. And we are going always to work with this table to understand the algorithm. So here is our acceptors, A1 to A3. We have 3 acceptors here. And initially we are here. All the acceptors have some initial value, which is like undefined value. But then we can have an arbitrary set of proposers. So this is the idea. So in this case, we have 3 acceptors and an arbitrary set of proposers.